In this section, we're going to apply some of our skills with logarithms and the exponential function. And we've already done that earlier in this section in a sense. I introduced this to you, I think, as the idea of an exponential function with the financial ideas. So let me refresh you with this. So if I was having an investment that is growing continuously, I gave you this formula where P stands for the principal and RT is the rate and the time. Well, the principal could be thought of as the initial amount. It's how much you started with. And so we're going to do this in some applications of growth and decay, but it's exactly the same. There's no difference between what's happening with your money growing continuously or what's happening in bacteria or the decay of carbon. They're all the same thing. So let's go through one of these. So we see here that a population of bacteria is doubling. So let's put this into the formula. They're telling us that we start with 10. And so it makes no difference here. We're calling this AE to the KT now. But it's exactly the same thing. Do you see it's PE to the RT? It's the same thing, where K is now representing the rate of growth. Well, this, or decay, and this was the rate in financial terms, same thing, time, time. A is going to stand for that initial amount, just like P was the initial amount of principal put in an investment. We're doing exactly the same thing. So they've told me that we have 10 whatever this is, grams of this bacteria, or 10 bacteria, and we want to see how long it's going to take to double. Same thing we already knew, just a new application. Okay, so we don't know that rate of growth, that K, that constant at which this bacteria always keeps growing. But we do know, we're interested in knowing, oh yeah, okay, so we know that after 1 hour it is doubled. So what we're trying to do here is find that rate of growth. We don't know it, and we're trying to find it. So I've got everything in. I know that after 1 hour, my time, I've got double the bacteria I had when I started. Well, now we know how to solve an equation like this. I'm going to get the difficult portion alone, that e to the k. I'm going to get that alone by dividing both sides by 10. Now I'm going to solve for k here by taking the natural log of both sides. So now I've got the value of that constant. What else do they want us to know? Okay, they wanted us to graph it, but I wouldn't ask you to do that. But so now we have the generic equation. The function equals 10, that initial amount, e. Now we know that rate, that constant k, and we could graph it for any value of t. This is the equation we want to create. Okay, let's try another one. This time our application here is the half-life of carbon, but it is exponential. It's the same idea. So look what they've done. Let's see what we got here. A naught is going to be called, that's our initial amount. And look what we've done. I know the half-life, which means that I know when I have 50% of that initial amount. So I don't actually know how much is at the end of this, but I don't even need to. I have 50% of the initial amount, and look what happens. I could divide both sides by A naught, and all I need is the 0.5. Are you following that? So initial amount, I know the half-life. Well, half means 50% of it. So look what I've done. I start with the full amount. I've got half the initial amount. Now we're trying to find the half-life. What is that rate at which it turns in from full to 1/2? So I'm going to solve it. I'm looking for K, and we know it's 5,730 years. Well, what is the rate that this is decaying? Let's solve for K. So I have an equation like this. Well, I have isolated the E. All I need to do now is take the natural log of both sides. That allows me to bring the exponent. Well, actually, they would cancel out here on the right. Divide both sides by 5730, and I've got it. That number right there is the half-life of carbon. The rate at which it's decaying is the natural log of 0.5 divided by 5730. And we know what a half-life means is that in 5,730 years, you'll have half of what you started with, and this is our rate. So we've taken that number and we've subbed it into the formula in a generic sense where there's our rate and there's our time. Now they actually crunch that on the calculator and they get this number here. It's just the ln of 0.5 divided by 5730. Okay, so let's try one here. So here's what I know. I have some initial amount of plutonium, but I don't even care. I'm looking for when will I have half of that amount left. So what I'm going to have is this. I'm looking, it's called K, but it's the same as R. That's all it is. And we're multiplying it. We're letting it go for 80 million years. And we know at the end of 80 million years, we will have half of what we started with. Okay, so you see the A naughts don't matter. I could divide it across, they would go. So I'm going to have this. All I've done is just rearrange it so it looks a little more normal. But I have the E isolated, so I can take the log of both sides. And over here, I just have this. So what is the half or the rate of decay for plutonium? Just divide both sides by 80 million. Easier said than done. ln of 0.5 divided by, I hope I have enough zeros there. Did I do it in 3? So yeah, I think so. So the ln of 0.5 divided by 80 million. So that's the rate at which it decays. So if you start with your initial amount of plutonium, well, let me put it into the original equation. So here's what I've got. Okay, so anytime I have the initial amount of plutonium and I see how long I've been going, for how many years, I could find out how much plutonium is left. That's what this formula is accomplishing. Okay, they're doing something clever here. Well, let me show you and then just kind of show you where it comes from. So a bone fragment, what they're talking about here is they're carbon-14 dating the age of a bone. So that's going to require the decay of carbon. Well, we've already found that. We know the decay of carbon is this number right here. So if we didn't know it, let me show you what we would do. So what we would be doing is we want to know when there'd be 20% left. That's what we'd be looking for. Well, we would need that K, and then we've got T. Well, we have K. We already found that when we found the half-life. So we're going to use that number that we saw before, which was this, the ln of 0.5 by 5730. But here's what's happening. They're jumping ahead. They know that those are going to drop out, and then they know that they could just take the natural log What they did is they've created another formula. It's really not necessary. It's just the same thing. But what they saw was they just jumped ahead for solving for t. That's all they've done. And so we're looking for this r in their formula is what percentage do we want to have left? Well, we want 20%. And then they're dividing it here by the rate of decay of carbon, which we solved when we found out that half-life question earlier. So this is the value of K that we found on the other screen. They just put it as a real number instead of logs. The ln of R is just solving, the R is standing for what percentage do we have left, 20%. So again, this looks like another formula, but it's not. They're just kind of jumping ahead a little bit. Now, it's useful. Let's see. Okay, I thought this was going to be the same question, but it's not. Okay, so we're going to start with 200 milligrams of cesium. Don't know much about this. We'll call it cesium. I think that's right. Okay, now we don't have K. Yeah, here's what we got. Well, you could do this a couple ways, but okay, so here's what we need. We need to find out how long it takes to get down to 1 milligram. But before we can do that, we have to complete our formula. And, oops, too many zeros. Okay, so this should be 100. So here's the information they've given me. We're starting with 200. The half-life is 30 years. So I know that at the end of 30 years, I'm left with 100, right? So if I divide that across, here's what's always going to happen. It's the half-life. So when I divide that, I'm going to just be left with 0.5. That's always going to be true. Okay, so I have this. All right, well, we have the e isolated, so let's take the log of both sides. So the natural log of 0.5 equals 30 times k. So k is then equal to the natural log of 0.5 divided by 30. Now I have that rate of decay. This is how cesium is decaying, at this rate. So now I have the complete formula. I've got my initial amount. I've got e to the natural log of 0.5 over, over 30. And our time is what we don't know, but we want to know how long it's going to take to get down to 1 milligram. Okay, so let's do just some math. Use our logarithm skills. So I'm going to have 1 divided by 200 equals e to the natural log of 0.5 over 30 times time. Now, if I take the natural log of both sides, I can take care of this problem part on the right. So I've got the natural log of 1 over 200 equals the natural log of 0.5 over 30 all times t. And I'm solving for t. So the natural log of 1 over 200 divided by the ln of 0.5 over 30 equals t. Okay, so we've got it. Now the question was, how long is it going to take? So we're going to actually need to crunch this down. So give me just a moment here as I divide this on my calculator. Okay, so the time it takes to get down to 1 milligram remaining, I got 1.294. And something is wrong. Give me a second to see if I can fix this. Something that didn't work out right. Okay, it took me a while to figure out what I did, but it's right here. So here's the value of k. It's the natural log of 0.5 divided by 30. And when I did this, I divided the 0.5 by 30 inside of the parentheses. So it should have been the natural log of 0.5 divided by 30. And when I do that, I get 229.3. Okay, so that's how many years it's going to take to start with 200 milligrams and get it down to 1 milligram. And the original question is, are we more or less than 230 years? We're a little bit less. Okay, so doubling time is the same exact question. Instead of going down to half, we're going up to double. So it creates the same thing. So let me show you what we would do here. So just like before, remember this is our equation. So k in this version. So here's our equation. We want to know when the amount at the end turns into twice what we started with. So it's exactly the same problem that we had before. So if I put this in here, you see the a naughts are going to drop out again. So I've got 2 equals e k to the t. Okay, so what do I do with this? Well, I would do the same thing. I would solve both sides. I'd be left with k times t. So if I want to know, well, we could do a couple things here. If I'm looking for the rate, I'm looking for k. Let me see what they're doing here. Yeah, no, they were looking for k. So if I want to know the rate at which I'm doubling, it would then be the natural log of 2 divided by t equals k. Oh yeah, and this one is saying it's taking approximately 2 years to double, so I know the value of t is 2. Okay, so what I'm trying to do, and I hope it makes some sense, is this is exactly the same. Instead of going down to a half, we're going up to double. And so the a-naughts drop out again. We're just solving it for k to see what is that rate that requires it to double. And you just divide that natural log of double divided by the time. It just so happens that it's a 2 again. That's just a coincidence. And now we have the formula for the doubling time because now I have the value of k. And we could then use this equation to see where we might be after any certain number of years. Okay. I don't. Okay, so I don't know what Moore's law really is about here. So that's what they're telling us. So here's what we had. This is what we found on the last page. That we're looking for that rate of growth. We saw the 2 stands for the doubling. And how long does that happen to take? Well, now they're saying it's changed to 3 years. So k is now the ln of 2 divided by 3. So if we wanted our amount, it has now become this. That's all. The rate is now divided by a time of 3 instead of 2. Okay, I think we have one more section of these applications, or a second half of this video, so hopefully that makes sense. We're really doing nothing new here. This is essentially what we already did with finances. We're just applying it now to exponential growth and decay for bacteria, half-lives, things like that.